Welcome back to Algorismo. We are thrilled to have you join us for another exciting exploration into the world of algorithms. Today, we are beginning a fundamental and fascinating topic: sorting. Sorting algorithms play a critical role in how we organize, access, and process data efficiently, and are the backbones that keeps our digital world in order. They are everywhere, in computer science and beyond, and we are about to unravel their secrets together. In our journey so far, we have been building a solid foundation with some essential search algorithms. The first video, Finding the Maximum Value, introduced us to the algorithm basics by showing how to locate the largest element in a list. The second video, Linear Search, taught us the step-by-step method for searching sequentially, and we analyzed how its efficiency changes as data grows larger. The third video, Binary Search, showcased the power of sorted data. Using a clever divide and conquer approach, we learned how to dramatically reduce search time with both iterative and recursive methods. Don't worry about the term divide and conquer, as we shall shed more light on it in coming days. Through these explorations, we discovered a key insight. Sorted data makes search operations faster and more efficient. Sorting isn't just a preparatory step, it's a powerful tool that enhances how we interact with data. Now we are turning our attention to the process of sorting itself. In this video, we'll introduce various sorting techniques, setting the stage for quicker searches and optimized data handling. We will see how different algorithms tackle the challenge of sorting and why choosing the right one matters. We shall then unravel the details of sorting algorithms in later videos individually. Let's dive in and explore the fascinating world of sorting algorithms. Imagine walking into your study room where books are scattered randomly on shelves. Finding your favorite book would be hard. Thankfully, you keep them sorted by genre or title, making it a breeze to locate any book you want. Remember those old library card catalogs? Those drawers filled with meticulously sorted cards were the keys to unlocking the entire library's collection. Each card held information about a book, and because they were sorted alphabetically or by subject, anyone could navigate the library with ease. Now think about your closet. You might hang your shirts, fold your pants, and tuck socks into a drawer. Maybe you organize clothes by color or season. By sorting your wardrobe, getting dressed becomes effortless. You now know where everything is. Sorting is all around us. It transforms chaos into order, saves us time, and reduces stress, helping us manage our daily lives more efficiently. It's the simple act of arranging things in a way that makes sense, and it makes all the difference. Let's dive into the digital world. Ever wonder how search engines like Google deliver the most relevant results most instantly? They sort through billions of web pages, ranking them by relevance so you get the best answer at the top of the list. When shopping online for a new dress, you might sort items by price, customer rating, or style. With just a click, thousands of products rearrange to fit your preferences, making your shopping experience smooth and personalized. On your computer, files are neatly organized in folders and can be sorted by name, date modified, or file type. This organization makes it easy to find that important document or favorite photo without digging through endless files. But sorting goes even deeper in computer science. In internet traffic routing, data packets are sorted and directed efficiently to ensure fast and reliable communication. Databases use sorting to index information, dramatically improving search speeds and performance. Operating systems rely on sorting algorithms for task scheduling and memory management. This ensures your computer runs multiple applications smoothly without freezing or crashing. Sorting is crucial in specialized fields too. In domains like data compression, cryptography, genome sequencing, gaming, load balancing, data analysis, image processing, neural networks, and machine learning, sorting is the unsung hero behind all of these. It optimizes performance, enhances user experience, and enables complex computations. Let's delve into the different types of sorting algorithms. Broadly speaking, there are two main categories: comparison based and non comparison based sorting algorithms. Comparison based algorithms are the most common. They sort data by comparing elements with each other. Within this category, we can make two groups. The first group of algorithms, for example, selection sort, bubble sort, or insertion sort, and many others, are some of the simplest algorithms and are great for understanding the basics. However, they generally exhibit the highest time complexity among the sorting algorithms, meaning they become inefficient as the data size grows. To be specific, these algorithms' worst case time complexity is O of n square. In the next video, we will better understand what n square means once we begin to unwind this class of algorithms. The second group of algorithms, for example, merge sort and quicksort, are more advanced and sometimes considered a little more complicated. However, this class of algorithms is efficient and has a lower time complexity. The specific term to represent their time complexity is O of n log n. And yes, we leave it for later to understand n log n and its comparison with n square. They can handle larger datasets much more effectively and are widely used in various applications. On the other hand, we have non-comparison based algorithms. Well, wait, can we even sort data or say numbers without comparing them? Yes, it is indeed possible. Algorithms like counting sort, Radix sort, and bucket sort fall in this category. These algorithms don't compare elements directly, instead, they use other properties of the data to sort them. Impressively, they can achieve the lowest time complexity compared to the comparison based algorithms. Well, what is the lowest time complexity that these algorithms achieve? Believe it or not, it is just O of n, or linear time, the same as for finding max and linear search. Having covered linear search and binary search algorithms, I hope you understand the concept of both linear and logarithmic complexities very well. It seems like that these non-comparison based sorting algorithms are a clear winner. But hold on, there is more to the story. It turns out that complexity is not the only determinant for sorting algorithms. We also have the dimension of applicability of these classes of algorithms to different situations. While non-comparison based algorithms are faster in terms of time complexity, they are applicable only to specialized types of data. For example, counting sort works best when we know the range of input data in advance and it's not excessively large. The algorithms from our first group, selection, bubble, and insertion sort, while simple to implement and understand, are practical for small datasets only. They get slower and slower as amount of data gets large. Our second group, merge sort and quicksort, are the real workhorses. They are applicable to almost all situations and are generally preferred because they offer a good balance between efficiency and versatility. Well, the story does not end here. See, insertion sort does not seem happy with this detail. It might feel a bit overshadowed by the likes of merge sort and quicksort, but it has its own strengths. For nearly sorted datasets, insertion sort can be surprisingly efficient and is often used in real-world applications where its simplicity shines. While keeping it in the same class, let's give a special shout out to insertion sort. So what's the key takeaway here? Choosing the right sorting algorithm can be intricate. It depends on various factors like size of data, the nature of data, and the specific requirements of the task at hand. There is no one size fits all solution. But that's the beauty of algorithms. We have a toolkit full of options, and the more we know about these, the better we organize and optimize our data. Thank you for joining us on this exploration of sorting algorithms. We hope you have now a clear picture of how sorting touches every aspect of data organization, both in our everyday life and in the digital realm. In our next video, we will dive deep into selection sort, one of the fundamental sorting algorithms. We will break down how it works step by step and show you how to implement it effectively, and will analyze its complexity too. So stay tuned and get ready to expand your algorithmic toolkit even further. Until then, keep exploring and happy coding.